Well, hello everybody, and welcome to this online class presented by Metcom. My name is Omar Arafat. I'm a project metallurgist with Metcom, and I'm going to be the moderator for today's class. I have with me Dr. Robert McIvor, the Chief Metallurgist at Metcom Technologies. We are so glad that you're able to join us today, and we're really excited to reach out to Mets and other industry people, and we want to use this platform to deliver our message on functional performance analysis, explain how it was developed and how you can implement it as a tool at the plants you're working at to measure and significantly improve grinding operations. So just some brief housekeeping and notes on the platform. We're using the Zoom webinar as our platform today to deliver this class. I'm sure many of you are familiar with Zoom or Zoom meeting, and the Zoom webinar platform is very similar with a few added features and controls. Today's class will consist of presentations and a couple of videos during which all the participants are muted. You can always use, there's a chat dialogue, and you can use that if you need to communicate with me at any time during the presentation. I'll do my best to answer you in real time. And then about midway through the presentation, we'll open up to a live Q&A session. You'll notice that there is a Q&A icon or Q&A button on the bottom of your toolbar on the Zoom screen, and you can use that to post questions, and I'll do our best to answer them, and I'll read those questions aloud as they come in. By way of introduction, today's presenter is Dr. Robert McIvor. Rob is founder and chief metallurgist at Metcom Technologies, where he has devoted his professional career to the design and optimization of mineral grinding circuits. Rob is the discoverer of functional performance analysis of ball mill circuits, which will be the focus of his talk today. So without further delay, I will turn this over to Rob.
Thank you, Omar. And thank you everyone for attending. I hope you're all keeping well and safe. This class is about ball mill grinding circuits. Grinding is one of the most poorly understood topics in mineral processing. Not just my words, but many colleagues that I have, both in operations and in the support businesses. Plant mets today have been provided very little help from the scientific community in terms of tools to aid them in their daily task of getting the most out of their grinding circuits. But just imagine you have a thorough and accurate understanding of the workings of a grinding circuit. And as a result, you also have control over how they perform in your plant. And in this series of classes, we plan to show you that with the right tools, that is entirely achievable. In the next class, we'll expose population balance modeling not only as the wrong tool, but as a waste of time and resources as far as making plant improvements is concerned. But let's start with a truly powerful tool, the functional performance equation for ball milling circuits. This simple equation breaks down the barriers to understanding the workings of the grinding circuit. And then we can put it to work to make the plant circuit perform in the best possible way for the operation. So let's get started. Let's go back to 1925 when Professor E.W. Davis of the University of Minnesota published work that he was doing. He was working with a pilot plant ball mill circuit, wet grinding ball mill circuit, in closed circuit with the classifiers used in those days. And he developed a famous curve showing the relationship between circulating load and the productivity of the circuit. Let's call up these slides here. So what you see on the screen now is that Davis relationship. He started by operating his pilot ball mill in open circuit, and the circulating load ratio is given along the horizontal axis here. So at 0% circulating load, that's open circuit. The reference productivity of the circuit was 100 units of new product size material, or you can also think of that in terms of the feed rate to the circuit. So this was with the same mill. By putting that mill in closed circuit with a classifier, and introducing a circulating load of first 100 and then 200% circulating load, the capacity of the circuit, first it doubled and then went up to 2.5 times the productivity in closed circuit with a circulating load of 400 to 500% than in open circuit, which is really remarkable. And of course, this is how we operate our ball mill circuits today, and to our tremendous and obvious benefit. Now, jump forward to the 1980s, where classification equipment companies like Linatech Corporation, where I was working at the time, we had developed cyclone and pump selection procedures to achieve desired ball mill circuit operating conditions, including a specified circulating load ratio. So we could help willing customers increase their circulating loads by adjusting or sometimes replacing the pumps and cyclones, and therefore provide them with a way to increase their circuit productivity. But we did not understand why this was happening until a breakthrough came in 1985 while examining size distributions going through the ball mills around grinding circuits with the same feed and product size but with different circulating load ratios. And in this slide, you see the cumulative percent passing size distributions of two circuits. These circuits were providing a cyclone overflow P80 size of 150 mesh or 106 micron. The circuit with the high circulating load, 500% circulating load, this was the feed size distribution and this was the product size distribution going through the ball mill. And the size distributions going through the ball mill with the much lower circulating load are shown here. And it's striking that these size distributions are very different. We can see that the high circulating load mill has much coarser material passing through it. In fact, you can see that about 15% of the material on average in the mill is finer, and 85% of the material is coarser than the P80, compared to about 72% of the material being coarser than the P80 for the low circulating load mill. And if we also look at Davis's circulating load ratio, as we increase the circulating load from 150% to 500%, we get about a 20% increase in productivity. And if we compare the percentage of coarse material in the mill at 500% versus 150%, it's 20% larger. So this is our eureka moment. The reason high circulating load is more efficient for the circuit is because it results in more of the mill volume, more of its grinding power being used on plus P80 size material. So, with this discovery in mind, we did some follow-up work for several years at McGill University to validate this finding. This led to a further breakthrough in knowledge about how the ball mill circuit functions, specifically the functional performance equation. And what this equation shows is that the performance of a ball milling circuit can be expressed in terms of 4 essential inputs. And this is described in the video that we're going to run now, which does a better job of explaining than I do myself. So Omar, if you want to cue up the video, please.
The functional performance equation is a new powerful tool for understanding, measuring, and improving the performance of ball milling circuits. The ball milling circuit consists of the ball mill, the pump, and the hydrocyclones. A very interesting observation about ball milling circuits is that operating them at high circulating load ratios makes them much more efficient. We can produce 2 to 3 times the amount of new product size material by operating in closed circuit with a circulating load of 300 to 500% than we can in open circuit. The question is, why? Observation of the size distributions in and out of the ball mill for circuits at high circulating loads versus lower circulating loads tells us why higher circulating loads are more efficient. The size distributions in and out of the ball mill in a circuit with high circulating loads are coarser than those operating with low circulating loads. We can do this comparison looking at the performance of two circuits with the same feed size to the circuit and the same product size out of the cyclone overflow. The one at 500% circulating load produces approximately 262 tons an hour of new finished size material, whereas the one with lower circulating load produces only 203 tons per hour. That's an increase of 29% at the higher circulating load. If we look at the size distributions going in and out of the same two mills, the mill with the high circulating load has about 71% of the material inside the mill coarser than the P80, whereas the one with the lower circulating load has about 55%. This is also an increase of about 29%. The reason why the mill is more efficient is because it contains a more proportional amount of coarser material. We can define for a given grinding circuit the overall classification system efficiency. It is equal to the percentage of coarse material inside the ball mill. That also represents the percentage of our energy that the mill is using grinding the coarse material. To carry out functional performance analysis of a grinding circuit, we make the following definitions. Coarse particles are those that need to be ground further. Fines are those that have already been reduced to the desired product size. And we typically choose the P80 as the size to distinguish between coarse material and fines. For any ball mill circuit, we can state that the production rate of fines or new product size material has to equal the power applied to the coarse material multiplied by the grinding rate of the coarse material per unit of energy applied to it in the mill. But we know that the power applied to the coarse material in the mill is the total power times the percentage of coarse material in the mill, or the classification system efficiency. We can therefore write the simple equation that the production rate of new fines or product size material for the ball mill circuit is equal to the total mill power draw times the classification system efficiency times the mill grinding rate of coarse material. Also note, by dividing the mill grinding rate by the ore grindability and multiplying again by the ore grindability to balance the equation, we are left with the ratio between the mill grinding rate of coarse material and the grindability of the same material in a test mill. This ratio between the mill grinding rate and the grinding rate in the standard laboratory mill is a measure of the ball mill grinding efficiency. So we can finally write the functional performance equation, that the circuit output of fines or new product size material is equal to the mill kilowatts times the classification system efficiency times the ore grindability times the mill grinding efficiency. And we see that there are two separate active efficiencies at play in a ball milling circuit, the classification system efficiency and the mill grinding efficiency. Now let's look at an example of how the functional performance equation is calculated and how it's used to study a change in the performance of a ball milling circuit. At the Cell Bay Copper Concentrator, a study was conducted to find out about the effect of a change in the grinding media on the performance of the ball mill. A circuit audit was carried out to measure the performance of the mill. During the initial survey, the production rate of new product size material, that is material finer than 106 microns, was 33.3 tons per hour. This was calculated from the tonnage to the circuit, the size distribution of the cyclone overflow, and the size distribution of the new feed coming into the circuit. The mill power draw was 523 kilowatts as calculated at the pinion. The circuit classification system efficiency was 71%. This was determined by taking samples of the ball mill feed at discharge and calculating the average amount of material coarser than 106 micron. The grindability of the ore was measured to be 2.31 grams per revolution as measured in a test laboratory mill, in this case, a bond ball mill. Since we have all the other factors, we can then calculate the mill grinding efficiency, which came out to be 38.8 kilograms per kilowatt hour per gram per revolution. Months after the grinding media were changed, another survey was carried out. This time, the production rate of a new minus 106 micron material was 30.6 tons per hour. The mill draw was 545 kilowatts. The percentage of coarse material in the mill, or the classification system efficiency, was 72.4%. The grindability of the ore was measured to be 1.43 grams per revolution. The overall mill grinding efficiency increased to 52.9, a substantial increase over the 38.8, and this is directly attributable to the change in grinding media. A second example of calculating the functional performance equation is taken from the dome gold milling circuit. The grinding circuit uses 2 stages of cycloning in addition to a lot of water that was added into the circuit because of the jigs. Comparison of the dome survey with the initial cell bay survey shows that the classification system efficiency as measured at the actual P80 of the survey was 85.5%. 85.5% of the mill energy was being used to grind material coarser than the P80. Compare that to the cell-based circuit where only 68.5% of the energy was being used. This tells us by manipulating the pumps and the cyclones and the water usage in a grinding circuit, we can increase our efficiency up to as high as 85.5%, sometimes higher. Here's an example of numerous surveys that were conducted at the Tilden Iron Ore Concentrator, studying the percent solids of the mill discharge and the mill grinding efficiency. 16 surveys were conducted over a period of several years, the initial 12 without intentionally varying the mill percent solids, then by increasing, and then finally reducing the water addition to the pebble mill. This relationship between the mill grinding efficiency and the percent solids in the mill was determined. It is statistically highly relevant. What it showed was that by reducing the amount of water addition to the pebble mill, the mill grinding efficiency increased. Such an increase provided major energy cost savings. Here is an example of the use of the functional performance equation to study the replacement of standard cyclones with modern high-efficiency cyclones in a sulfide flotation concentrator. The survey data in the first equation shows that the classification system efficiency was 56.6%. With new cyclones, circuit modeling showed that this could be increased to 60.9%, an overall increase in efficiency and circuit production rate capability of 7.5%. In addition to the benefit of classification system efficiency, the cyclone overflow product size distribution was significantly narrower, reducing the amount of coarse particles going to flotation at the same grind P80. Installation of the high-efficiency cyclones took place and the benefits were achieved exactly as predicted. In another study for a gold ore processor, the amount of water being added to the cyclone was varied to create different cyclone overflow percent solids. varying from a high of 50%, which would be typical for a CIL circuit feed, to as low as 10%. We know that by doing this, we increase the cyclone efficiency. And by doing so, we were able to increase the classification system efficiency from the mid-60s all the way up to the mid-80s, even 86%. This showed us that by installing a thickener after the grinding circuit, for example, to deal with all the extra water ahead of CIL processing, that the efficiency of the grinding circuit could be increased by approximately 30%. The thickener was installed, and the grinding circuit significantly outperformed all previous production. There are many examples of the successful use of the functional performance equation in mineral processing plants today. Here is just a short list of some of them. Every one of these is taken from actual plant experiences, and all provided efficiency improvements resulting in major financial benefits for these companies. The functional performance equation is an excellent tool for making improvements to plant grinding circuits. First of all, it is very simple. Secondly, it is very accurate. Thirdly, it clarifies our understanding and quantifies ball mill circuit performance. It recognizes that there are two separate active efficiencies in play: the circuit classification system efficiency and the mill grinding efficiency. And it quantifies them for us. That is, provides the metrics to measure and see improvements. Next, each efficiency is clearly linked to specific plant design and operating variables. The circuit classification system efficiency is related to the setup of the pumps and the cyclones. The mill grinding efficiency is related to factors like the ball size and the percent solids in the mill. Next, this equation provides us clear optimization criteria. We want to maximize the circuit classification system efficiency, and we want to maximize the mill grinding efficiency. And finally, it provides a strategy and a clear plan for plant optimization work. We conduct an audit and complete the functional performance equation. We then look at ways to change the pumps and the cyclones or the operation of the ball mill to improve their performances. We implement those changes, and then we go back and do another audit to see how we've done. The functional performance equation is indeed a breakthrough, a new tool that allows us to better understand, to better measure the performance, and to improve the efficiency of ball mill grinding circuits. We are grateful to McGill University and the many industrial companies who have contributed to the development and use of the functional performance equation.
Okay,
Okay, thank you, Omar. Am I back on the screen?
you're back online.
Okay, thank you very much. For everyone who's listening, if you want to review that video again, it's available on our website. You can go there and review it at any time, show it to your colleagues. There's also a recorded seminar on our website that just focused on classification system efficiency. And you're welcome to go and look at that one as well. There's also published papers, awards, and other things, all related to the functional performance equation for grinding circuits. So let's open it up for questions, Omar, before we go on to the next topic, which is how do we go about ensuring that the functional performance equation can be well exploited by plant operations?
Great. So yeah, I'll ask that you use the Q&A button to pose questions, and then I'll verbalize the questions and pose them to Rob. Alejandro put a question into the chat box. How is it possible that with a higher circulating load we'll have better CSE? What I know is that a higher circulating load would be because of bad classification of the cyclones. So the efficiency of the circuit would be poor because of that. So I guess he's asking high circulating load to have a negative impact on the classification efficiency.
Yeah, a high circulating load, in fact, means that there's high density at the cyclone and that the separation performance of the cyclone is indeed not as good. The bypass fraction is higher, so that's not good. But the net overall effect of shortening the residence time in the mill so that there's very little overgrinding taking place, even though the hydrocyclone may not be performing itself as with such a sharp classification, the net steady state case with a high circulating load is that the material is getting to the cyclone very rapidly in the circuit, such that the fines are being removed from the circuit very rapidly, and the net steady state situation is a much coarser overall size distribution inside the ball mill, which is high CSC. Think of an infinite circulating load, even though say the cyclone isn't performing that efficiently. With an infinite circulating load, every particle, the instant it's formed that's finer than the P80, is removed from the circuit. So even though the classifier is not performing that sharply, the net effect of the high circulating load is an overall increase in classification system efficiency. The net effect is a higher percentage of coarse material remaining inside the circuit.
Great. I have another question asking does functional performance apply to sag milling?
That's a good question, and in all likelihood, it does. If we know a sag circuit with say a 10 millimeter screen is producing material through that screen size at so many tons an hour, we know again, because it's because of the power of the mill that's applied to the material coarser than 10 millimeter and its grinding rate. However, in a ball mill circuit, by sampling the mill feed and discharge, we can estimate the contents of the mill. We can't do that with the sag mill because of the grate. We just don't know the size distribution inside the mill, and therefore we can't calculate the percentage of plus screen size material. So it's undoubtedly true for a sag circuit, but we don't have the tools to measure the size distribution inside the mill. If we did, we could apply it to sag milling as well.
Okay, from John's asking, is a high circulating load efficient for producing a coarse overflow grind target size or coarse overflow grind P80 of say 250 to 300 microns?
Yes, it is. We've looked at quite a few circuits in western part of the United States and Canada, porphyry coppers, where the grinds are typically 200 to 300 microns. The feed size to the ball milling circuits is typically, say, minus 10 millimeters from a sag mill. And yes, it still applies whether we're grinding to 200 microns or 300 microns or 65 microns or 75 microns. The same principles apply. We look at the P80 and do the calculations based on the P80 of whatever the target P80 of whatever the circuit is, and go from there. And it works just fine for coarse grinding circuits as well as fine grinding circuits.
Okay, Alejandro's asking, with the high circulating load, will the mill be overloaded? That
will eventually happen. We've done surveys on small mills where the tonnage is fairly low. So even at a very high circulating load, the flow rate and the buildup of coarse material in the mill is not that great. And we've seen that the classification system efficiency increased all the way up to a circulating load of 800%. It was in the high 80s, where a very, very high number. And when you get to the large mills, the buildup of coarse material and the high flow rates eventually cause the charge to swell, and you start to lose some power of the mills. So we reach a constraint with these large mills where the circulating load gets to a certain point and then it does cause the mill to overload, or it can cause the mill to overload, depending on other conditions like the coarser size of material building up in the mill and the size of the grinding balls managing that and so on. But yes, large mills especially will tend to overload if the circulating load goes very high, say above 400 or 500%. So in those cases, we have to be careful. We have to see at what point might overloading take place and then constrain ourselves within that boundary.
Okay. Can functional performance be used with screens or other classifiers in the circuit, or is it strictly cyclones?
It can be used with any classifiers. The cyclone is typical, but we've also done plant audits where screens are used. So typically it doesn't matter what the nature of the classifier is. Now, screens behave, heavy minerals behave much differently on screens, which separate strictly by size. Heavy minerals can build up in a circuit with hydrocyclones. For instance, if you have a magnetite, which is a gangue mineral, that can be very bad for building up inside the ball milling circuits. And in that case, replacing the cyclones with screens can be very, very beneficial. But yes, the functional performance equation and classification system efficiency does not depend on the type of classifier that you use.
Okay, I think we have time for one last question. This question relates to grindability testing, as indicated in the functional performance equation. Does that need to be a bond test, or are other grindability tests can be used in this in the equation?
It can be a bond test, or it can be any on-site batch grindability test that is set up at the operation. The only requirement is that each time you do the grindability test, it's repeated exactly the same way. So a bond test is done on circuit feed, and that's where we get the grindability in grams per revolution. Very often when we're doing plant site work, we set up an on-site batch grindability test with whatever ball mill they have available. Well, with a grinding charge, we typically do it dry. And rather than a lock cycle test on circuit feed, we do a batch test on actual ball mill feed, say the cyclone underflow. We take a sample of that material, we put it in the mill, we grind for 1 minute, and we get the grindability in terms of grams per revolution of the material. We measure the grindability. So either way will work just fine when you're doing functional performance analysis, as long as you measure it exactly the same way when you're comparing one survey to the next.
Great. So we can continue forward.
Okay, thanks, Omar. How can one be assured that this tool will be used successfully in any given plant site? There are clearly quite a number of essential accompanying steps that are needed in order to put it to work. All the right information on the circuit equipment has to be collected. The circuit must be sampled properly to do the audits. Steps to manipulate the pumps and cyclones properly have to be learned and carried out. And the costs of doing all these steps need to be justified by the expected financial returns. So to address all these questions, a partnership was formed between 2 operating plants, a number of grinding specialists, including myself, and experts in the design of training programs. So the objective was twofold. First, it was to lay out all the steps that were needed in order to achieve plant grinding improvements using the functional performance equation. And then secondly, to take each of those steps and then put them into a training program. And that's covered in the next video. If you want to cue that up, please, Omar.
Faced with the many challenges of successfully making plant grinding improvements with the use of the functional performance equation, a team was formed with 2 milling operations, grinding technical experts, and instructional design specialists. The result of these efforts is Metcom's management system to improve plant grinding performance. In this presentation, we will cover an introduction to management systems, the task analysis to determine the needed components of the system structure, and development of the training program for delivery of the system into operations. The functional performance equation provides new opportunity for making plant grinding improvements. However, a multitude of tasks are required to gain benefits from its use. Things such as accurate data gathering, including circuit sampling, monitoring and monetizing efficiency gains, knowledge of how to make cyclone adjustments, and many others. We recognized that we need to list, develop, and organize all the necessary steps in order to achieve plant grinding circuit improvements with this new tool. A textbook on management systems defines them as follows: the collection of all the required steps that ensure an organization will achieve defined objectives. Systems, or the systematic approach, are very common. Examples include the company organization chart that lays out roles of employees as they report to work each day, or your automobile, your transport system that gets you from home to the office in the morning. These systems can be complex and highly structured with many components and subcomponents. When combined, they can greatly improve the effectiveness of our work, but they can fail from just one weak component. An otherwise perfectly working automobile cannot function at all with just one wheel missing. Our objective is to improve plant grinding performance. We need to list, develop, and organize all the steps needed to improve plant grinding performance with this new tool. This collection of steps will be our Plant Grinding Process Improvement Management System. Task analysis. We need to address the question, what are all the steps needed to successfully use the functional performance equation to the maximum benefit of the operation? Task analysis is a process used to define and detail out those steps. A team made up of milling operations, grinding specialists, and instructional designers worked on this for 3 years. The outcome of all this work follows. Results of the task analysis. The final 13 components of the system. Measure circuit ore tonnage. Measure size distributions. Measure and achieve desired mill power draw. Measure ore resistance to breakage. Determine circuit overall work index efficiency. Tabulate direct grinding costs and define circuit product value. Apply functional performance. Determine ball mill circuit classification system efficiency and ball mill grinding efficiency. Optimize primary grinding within the context of the overall circuit. Achieve desired slurry pump performance. Achieve desired cyclone performance. Achieve desired ball mill conditions, such as media size and water addition. Conduct circuit sampling surveys. And finally, implement grind control. Unknown to us when initializing the task analysis, all the steps fell into one of 3 categories. First, information and measurements, both existing data on the plant equipment and the additional information and measurements required to conduct the technical analyses. Next, design, which encompasses all the steady-state relationships between circuit inputs and outputs. Subcomponents of design fall into energy efficiency, energy input, or mill power draw characteristics, and circuit product quality, in terms of recoverable metal in the downstream process. And finally, grind process control, to ensure that desired operating conditions and desired grind size are maintained with changing ore conditions. Together, these manage all the technical and economic inputs needed to maximize plant profitability with grinding circuit improvements. Finally, by definition, the Metcom Grinding Process Improvement Management System is the structured collection of all the steps and methods needed to measure and improve plant grinding circuit performance using Metcom and other needed metrics. What about system delivery? This is provided by means of a training program. Instructional design specialists initially supervised the task analysis. They then conducted learner and context analyses, and subsequently applied the instructional design process to develop the needed training modules and complete the program. The instructional design process is the management system that these specialists use to ensure that the training program works. That is, provides the skills to execute the grinding improvement process. Task analysis is joined by learner analysis, which outlines the attributes like language and education level of the audience, and context analysis, which describes the learning environment, primarily the location. Specific objectives, such as exactly what the learner will be able to do as an outcome of the training, are written for each of the training modules. Subject matter specialists write the first drafts, including examples and exercises. These are tested on a group of typical learners whose feedback is used for revisions. The process is repeated until each module demonstrates that a new learner can carry out the stated module objectives as shown by a certification test. A total of 21 training modules encompassing the 13 components of the grinding process improvement system were developed over the initial 3-year period. This training includes topics such as mill power and charge level measurements, work index efficiency calculations, functional performance analysis of the ball milling circuit, economic analysis of efficiency gains, hydrocyclone and pumping systems, and how to carry out plant sampling surveys. The training also includes how to properly analyze samples, conducting grindability testing, carrying out mass balance calculations on the circuit, how to evaluate the classification system efficiency, or CSE. Both the plants that participated in the initial program development and the first few new subscribers to the program used rod milling ahead of their ball milling circuits. The Ag-Sag milling module was subsequently added due to its popularity. To ensure that needed skill sets are provided to the typical players in plant process improvement work, a curriculum of training for plant personnel is recommended. However, a sole grinding champion can bring the system to success, particularly in a small operation. Likewise, implementation support can come from outside consultants or equipment vendors who have become popular subscribers to the training. Advantages of this training approach include ensuring all components of the system are provided. Skills achievement are verified through certification testing. The training system standardizes terminology, data collection and calculation forms, and reporting. The training system is fast to learn, easy to use, and helps to increase operating profit. It's cost-effective, particularly due to its online delivery, and the training provides lifelong knowledge for increased job satisfaction and career growth. Some features of the training. Learner prerequisites are secondary school language and math. It is web-based, self-taught, self-paced, and interactive. The training has been reviewed and accredited for continuing education credits. 6.4 CEUs for the complete program are granted by the Engineering Institute of Canada upon completion. And it's available in English, French, and Spanish, and subscribing companies are widely located. Major subscribing companies are provided their own online training access portal, where multiple staff have completed programs at one or more properties. Here are some of the cost savings on energy and grinding media from some published success stories. For example, optimizing percent solids in the pebble mills at Tilden gave a 5% efficiency gain in those mills, 3% for the overall ag plus pebble milling circuit. At 75,000 tons per day, the electrical energy cost saving is close to $2 million per year. Improved pebble sizing likewise saved another $5 million per year in electrical energy cost. Driven by the opportunity provided by the functional performance equation for ball milling circuits, a management system was developed to help operating plants increase grinding circuit efficiency. It is both technical and economic, and it was developed for industrial plants by working with industrial plants. It provides practical tools that plant staff can immediately put to use. It is delivered online through a comprehensive training program. Application of functional performance analysis has been widely successful, and contributions to plant profits are well documented. Metcom is pleased to have been given the opportunity to help bring this technology into the industry with the help of program developers and its industrial sponsors.
Thank you, Omar. So I'm back up.
You're back up.
We can now entertain questions either on the first part of the class today on the functional performance, or the management system or the training program, or whatever the audience would like to question.
Sure. And yeah, feel free to use the Q&A button on the bottom of your screen to put some questions forward for Rob. We have one question left over from the first Q&A from Alejandro. He's asking if we ever worked with KVEX cyclones from Weir, and compared them to say the Krebs, the GMAX cyclones.
We've worked with both of these, not necessarily in direct comparison with one another, but in comparison with older style cyclones, and replacement of older style cyclones, like the Krebs D10 models and so on. The newer design cyclones, both the GMAX and the KVEX and others manufactured by other equipment companies, are better. They've been designed using modern technology to improve the flow characteristics. As a result, they have sharper classification, and they also have lower pressure drop. So with the same pump, you can get a higher flow rate, and that opens the opportunity, if you replace old style cyclones with any of the modern cyclones, it gives you the opportunity to increase circulating load or increase water usage, which can lead to increased classification system efficiency. So yes, we've worked with both style of cyclones, and I think if you do a side-by-side comparison of KVEX and GMAX, you would get very, very similar results.
Great. One more question here. What would be a good practical circulating load ratio to target for a typical ball mill circuit?
We've actually done an economic analysis of the to determine the optimum economic circulating load ratio. As you increase circulating load, the benefit starts to trail off. So say you go from 400 to 500%, you do get an additional benefit in terms of milling energy, but your pumping costs go up, your wear goes up, and your downtime in the circuit for replacement pumps and cyclones also goes up. So those things all have to be traded off, and we found typically a circulating load certainly above 300%, and probably a maximum of 400 to 500% is usually close to the optimum economic value. If you have a very soft material like some limestones that don't really cause a lot of downtime because of wear, it's probably higher, more like 600% circulating load.
Okay. And what can an operation typically expect in terms of overall efficiency improvements?
Well, we've done dozens of plant studies starting from square one, and come up with efficiency gains in the ball milling circuit from a few percent, sometimes 3 or 4%, by replacing cyclones, let's say, with high efficiency cyclones, and up to as high as 30%, where there was increase in circulating load and also water usage of the cyclones. So there's a wide range of improvements that come about. Typically 10 to 15% overall would be great, and we're happy when we can get that. And that's fairly typical. But as again, they could be higher and it could be lower.
And what does the increased efficiency mean? Does that necessarily mean increased throughput?
When we find a way to increase efficiency, there are several ways to exploit that. In fact, this is covered in one of the training modules on grinding and plant economics. There's 3 things that you can do with an increase in efficiency. You can increase tonnage, sometimes, as long as there's no other constraint on the tonnage through the plant, either because of ore available from the mine or a tailing system. But most operators are looking for increased tonnage. And if the constraint in your plant on your site is the grinding circuit, then the most common way to exploit a 10% increase in grinding efficiency is a 10% increase in tonnage. A second way, if you're say limited in tonnage, the second way might be to grind finer if that finer grind gives you better performance downstream. If grinding a little finer gives you higher recovery of gold or copper or whatever the metal is you're processing. So the economics of that are often very favorable. If you have already, you're limited in tonnage and you're limited in the fineness of grind, you can always reduce your operating costs. So with a 10% increase in efficiency, you could reduce your energy consumption by 10%, and you will also reduce your media consumption by approximately 10%, because those are the 2 major costs associated with grinding. And those cost reductions, you can always get those benefits. Those were the benefits that were described in one of the slides. You can always calculate the benefits in terms of energy and media savings. But if the benefits can be used to increase tonnage or to grind finer, then you would opt for that if that is better economically for the plant.
Okay. Looks like Alejandro has another question. I guess in terms of overall improvement, efficiency improvement, do we want to look at the liners, changing the mill liners for efficiency gains?
Our experience is that ball mill liners have very small, not measurable effect on grinding efficiency. They do significantly affect the power draw by making the mill smaller when you replace worn liners with new liners. And so you typically get a drop in ball mill power draw with new liners. As long as the liner design is reasonable, the lift is reasonable and the thickness is reasonable and the mill speed is within the normal range, somewhere between 70 and 80% of critical speed, that we don't see the effect on grinding efficiency so much by the liners themselves. Liners are more a question of maintaining mill power draw and, of course, wear life, because they're costly to replace.
Okay. John's asking, what are the most critical variables to optimize cyclone performance?
Well, John, there's cyclone performance and there's grinding circuit classification system efficiency, and they're not the same thing. And in terms of the importance of getting the most out of your grinding circuit, that is maximizing the classification system efficiency, The most important variable is circulating load ratio. That's a 10. Now a second variable is the water balance at the cyclone. By adjusting the pumps and cyclones, if we can put more water into the cyclones and reduce the bypass, we can get a significant increase in classification system efficiency. Whereas circulating load is about a 10, the water balance might be 2 or 3 or 4 points. Or if you can, for instance, reduce flotation feed density from say 40% to 35%. In the one example given in the slideshow, the introduction of a thickener after a gold grinding circuit ahead of CIL was much larger than that. But typically, being able to use a little bit more water in the cyclones gives you something like 2, 3, 4, 5% improved efficiency. Finally, there's the sharpness of the classifier itself. So here we're talking cyclone efficiency itself, or sharpness of separation. And the net benefit of a very sharp classification versus a not so sharp classification is small in reality, and it surprised us. It's probably in the 1 to 2% benefit range. So again, in order of importance, circulating load first, that's a 10. Water balance is a 3 or a 4 or a 5. And then finally, the cyclone sharpness of separation, which is maybe a 1 or a 2. Now, the cyclone design can also be important because if it's a very efficient cyclones in terms of flow characteristics and has a good low pressure drop, then you can increase the flow and thereby increase water usage or circulating load ratio. Same pump. And the pump is almost always a constraint on how much you can do with your classification system. I hope that answers your question, Alejandro.
Okay, I got a question from Brant. Where can the functional performance analysis be applied to a brownfields project, which is currently offline and doesn't have very much operating data to provide?
Well, data is a requirement of the system. We talked about a management system has certain parts and essential components, and without those components, the system breaks down. So, for instance, we're adamant. Some people call us anal about sampling. We absolutely have to get good data from the circuit. So, if you have some data that shows an extremely poor situation, like the grinding balls are grossly oversized, or the circulating load is extremely low, then in a brownfield restarting, you could redesign around a higher circulating load or a better wall size. But in reality, we need to get a detailed, accurate plant audit done to well apply the functional performance equation. So there would be a limited amount we could do in the brownfield, depending on what information is available.
Okay, we have time for one last question. Steve's asking, how do you determine classification system efficiency if you can't sample the ball mill discharge? I guess that ties into the data comment that you said.
Right, that's a very good question. And the answer is you cannot. There's no substitute for having the information around the milling circuit. Well, sometimes it's possible you can get a material balance from sampling the circuit new feed and the combined cyclone feed, usually not. But sampling of the mill feed and mill discharge is, in every case, it's been necessary. And if you can't sample it, you have to make adjustments to the access to get that sample. And there's many ways to get at sampling. One thing we've done very often is to take a fairly small sample cutter and take slices of that stream, multiple slices to make up a complete sample. we haven't been stymied yet by not being able to sample a stream, but a considerable amount of work might have to go into that. Again, it's part of the system. We need the data. Without the data, the system collapses.
Great. So I think we're just approaching the hour now, the end of the hour. So this will conclude our class for today. Thank you so much for attending. We hope that you found it helpful and has gotten you thinking about how you can use functional performance as a tool at the plants that you're working with. If you'd like to learn more about functional performance and our system and the Metcom system, we'll be sending out an email shortly with some more information on our training program. And we also encourage you to visit our website to get some more information there. We hope to see you at our next online class, which will be announced fairly soon. And thank you, and everybody stay safe.
Thank you, everyone.
Thanks.